Hello, dear students. Today we are going to speak about Chapter 12, Chemical Bonding. The forces that hold groups of two or more atoms together and make them function as a unit is what we call chemical bond. The bond energy is the energy that is required to break a chemical bond. We have two types of chemical bonds. The first one that we are going to study is the ionic bonding. The ionic compound result when a metal reacts with a non-metal. Then remember, metal and non-metal. Remember that we always write the metal at the beginning and the non-metal at the end. The electrons are transferred from one atom, from the cation, from the metal to the non-metal. And at the end, we have the ionic compound because of a transfer of electrons. In the covalent bond, there is not transfer of electrons, but the atoms share the electrons. Let's see a polar covalent bond. A polar covalent bond is when we have two atoms with different electronegativity. Both are non-metals. Then the electrons are closer to the atom that is more electronegative, and you find like a delta negative charge. Is not a charge like in an ion. It means that you have more density of electrons around fluorine, for example. In this case, that is more electronegative than hydrogen, than in hydrogen, that you have less density of electrons. So you find here in hydrogen like a delta positive charge. It's not exactly a charge, it's just certain uh, higher density of electrons and certain lack of electrons. Here you have a question. You are going to stop the video here. You answer the questions. They are very, very important. Well, the electronegativity. What is exactly the electronegativity? It's the relative ability of an atom in a molecule to attract shared electrons to itself. In the periodic table, electronegativity generally increases across a period and decreases down a group for representative elements. The most electronegative atom is fluorine, and the less electronegative atom is cesium. Let's see. For example, here we have fluorine. The electronegativity of fluorine is 4.0, while the electronegativity of francium is 0.7. So we can see that the electronegativity of the metals, the representative metals, is very low. It's lower than 1.5, while the most electronegative atoms, the electronegativity of these atoms are between 3.0 and 4.0. Which one are the most electronegative atoms? Well, fluorine, oxygen, and nitrogen in this order. And we are going to see how important is to know the electronegativity of these atoms in order to make what we are going to study later that we call hydrogen bonds. Even though chlorine has similar electronegativity to nitrogen, because chlorine is a bigger atom than nitrogen, then this electronegativity has a different behavior. And for example, there are not hydrogen bonds with chlorine, while we have with nitrogen. And here you can see that the light blue color elements are the electronegativity of these elements that are all of them are metals, uh, except boron. Well, the electronegativity is between 1.5 and 1.9. And these atoms in um, a, a, a darker blue, the electronegativity is between 2.0 and 2.9. You can see here some non-metals and these transition metals and the hydrogen. And the most electronegative are, as I told you before, the ones in violet. If lithium and fluorine react, which has more attraction for the electrons, then you go here, lithium and fluorine. Well, lithium is here, 1.0, and fluorine is here. Of course, fluorine has a highest or higher electronegativity, so fluorine will attract the electrons to itself more than lithium. In a bond between fluorine and iodine, which has more attraction for the electron? Of course, fluorine, because the electronegativity of fluorine is higher than iodine. Well, here you have the question that we already answered, the general trends across the periodic table. As I told you before, to the left in a period, the electronegativity increases, while in a group, when you are going down, the electronegativity decreases. And for example, from fluorine across the periodic table until francium, the electronegativity decreases to the right, to the left, sorry. Here you have another question. The answer is already here, but you can stop the video and answer it by yourself. Here you have another one. Well, in this case, I'm going to stop because when the atoms loses electrons, they are smaller because they have less layers of electrons around the nucleus. That's what happened to oxygen plus 2. Oxygen positive is higher, then the radius is bigger, and oxygen is here, and oxygen minus 2 is the largest. This is the largest, radius, and oxygen plus 2 is the smallest radius. This is the answer for this question. Well, here we have in a covalent bond that you have two identical atoms as they have the same electronegativity, the bond is non-polar. But when you have two electrons that are non-metals and they share electrons, but one is more electronegative than the other, the electrons will be closer to this one than, than this one. So there is certain polarity in this kind of molecules, even though they are covalent, we say they are polar covalent. While in this case, we say that they are pure covalent because they are non-polar. And of course, in ionic compounds, we have a cation that is positive and an anion that is negative. So, of course, they are completely polar. Well, as I told you before, the relationship between electronegativity and bond types is the following one. When the difference of electronegativity between the atoms in the bond is zero because they are the same type of atoms, we say that the bond is covalent. And it has a higher covalent character and very low ionic character. In the other hand, we have large difference of electronegativity. In this case, we are in front of ionic bonds. Of course, the ionic character is very high and the covalent character is very, very low. And in between, we have the polar covalent that are two nonmetals that share electrons, but one atom takes closer, attracts more the electrons to itself than the other one. Which one? The most electronegative. Here we have a question. Arrange the following bonds from most polar to least polar. What are you going to do? Well, you're going to go, for example, here we have nitrogen and fluorine. You go to the table of electronegativity. Here we are. Here you have fluorine is 4.0 and nitrogen is 3. Then you come here, and now you say 4.0, sorry, minus 3.0, the electronegativity, the difference of electronegativity is 1.0. Then, same way, you find out the difference of electronegativity in each of the atom, and then you will go from the most polar, when the difference is higher, to the least polar, that is when the difference of electronegativity is 0 or close to 0. This is the way you can answer this question. Okay, here you have some questions. You will stop. We are going to see now what is the dipole moment. Well, here you have hydrogen and fluorine. The electronegativity of fluorine is the biggest one, and hydrogen has a lower electronegativity than fluorine. That's why we write here delta negative and here delta positive. What we do? Well, we make an arrow across the molecule, and the arrow will be in the direction of the most electronegative. That is what we call dipole moment. The dipole moment representations has an arrow in the direction of the most electronegative atom. What happened here? Well, in this case, we can see that the water molecule is a dipole because oxygen is delta negative and hydrogen is delta positive. Then when in water we put a cation, the dipoles, the water dipoles, takes this direction. The negative part are close to the cation that is positive, as you can see, and in the opposite way, when we are in front of an anion, the dipoles, the direction is the positive part of the water molecule is in the direction of the anion. That's why water can dissolve most of the compounds and is known as the universal uh, solvent. Well, the the group one, remember the group one always are metals and they make cations positive one. Group two, they are also metals and they make cations positive two. Aluminum always form the 3 plus cation. Group 7 nonmetals always form anions -1. And the group 6 elements always form -2 anions. The The atoms in stable compounds of the representative elements have a noble gas electron configuration. The metals lose electrons to reach the noble gas configuration, and the nonmetals gain electrons to get the noble gas configuration. For example, here we have that the neon is a noble gas and the configuration is this one. If we go to sodium, this is a configuration. Well, look at this. This part of the representation is the same one as neon. So we can represent in a short way using neon, and then the valence electrons that in this case we have one valence electron is the one that is loose in an ionic compound. Then in order to um, make stable elements, for example, sodium loses one electron, so we represent that this electron, that is the valence electron, is lost, and then sodium gets the um, configuration of neon that is very stable. Why we say that is very stable? Because they have 8 electrons in the outermost shell. That is the most stable configuration in the periodic table. Magnesium, same way, but as magnesium has 2 valence electrons, well, magnesium prefers to lose the 2 electrons and make a cation and get then the noble gas configuration that is more stable, and so on. The representative main group metals form ions by losing enough electrons to achieve the configuration of the previous noble gas, while nonmetals form ions by gaining enough electrons to achieve the configuration of the next noble gas. Here we have the configuration for groups 1, 2, and 3 usually form or lose, they lose electrons to get the noble gas configuration. While the nonmetals, they share electrons, and this way they complete the valence electron configuration of both atoms. For example, hydrogen has 1 electron, and another atom combines with this, and now they have 2 electrons that correspond to the configuration of helium, that is the noble gas in period 1. In other periods, of course, as I show you, for example, sodium that is in group 3, in period 3, usually loses 1 electron, and they get the corresponding noble gas configuration, that in this case is neon. Okay. Here we have chemical bonds that are always electrically neutral. For example, these are the cations for group 1, group 2, group 3, group 4, group 6. These are the anions, and group 7, these are the anions. And this is the electron configuration that the atoms in this period try to get. In this period, they try to be like neon. In this period, they try to be like argon, and so on. Here you have a concept check exercise. You stop the video. The answer is this one. Here you have another one. Well, the structure of ionic compounds, large amounts of energy are required to separate ionic compounds because the attractions between the cation and the anion are electrostatic, and they are very, very strong. That's why they make a structure like a solid, and the ions are packed together in such a way that maximizes the attraction of the opposite charged ions. Here we have different cations and different anions. As the cations are always smaller than the atom, and the anions are largest than the atom, because as they gain electrons, they are larger. As cations lose electrons, they make smaller cations. Ionic compounds containing polyatomic ions. Polyatomic ions work in the same way as simple ions. Covalent bonds hold the individual polyatomic ions together with all the atoms behaving as a unit. Then, for example, if we have chloride is a single unit, then, for example, NO3, that is a polyatomic ions, all the ions here has the behavior as a unit. Let's study the Lewis structure. It's a representation that is also known as dot representation. In the Lewis representations tries to, or is based on what we call the noble gas electron configurations. And in this case, they try to get an octet, or they try to get a duet. For example, for hydrogen, as they are in group or period 1, they try to get a duet like this. But in the case of other atoms, for example, as I showed you before, sodium tries to lose 1 electron, then is positive charged, and then it gets 8 electrons in the inner part of the atom. This octet, 8 electrons, is what we call the noble gas electron configuration is an octet. Then sodium tries to get an octet, and hydrogen tries to get a duet. For example, fluorine. Fluorine, what's going on with fluorine? Fluorine needs 1 electron. When fluorine combines with another atom of fluorine, this atom gets 8 electrons, but this atom also gets 8 electrons. Then both make the octet. And the molecule of fluorine is not in the normal way in form of atom, because this is not stable. This is not a stable configuration. That's why 2 atoms of fluorine always combines in order to make the molecule. The molecule is stable, while the atoms are not stable. That's why many atoms used to be in diatomic molecules form. Let's see how we can make the Lewis representation. First of all, we sum the valence electrons of all the atoms. Remember, the valence electrons are the electrons in the outermost shell of the atom. For example, for sodium has 1 electron. This is the valence electron. But for chlorine, for example, has 7 electrons in the outermost shell. So this, if we are going to make a compound using these two elements, we have to count the valence electrons of all the atoms. In this case, is 7 electrons. Sorry, 8 electrons. 7 from chlorine and 1 for sodium. Then you use 1 pair electron to form the bond. For example, here we are. In the water molecule, we know that we have 2 atoms of hydrogen. Every atom of hydrogen has 1 electron, valence electron. And you have also oxygen. Oxygen has 6 valence electrons. Then how much valence electron you have in total? You have 8 valence electron in total. What is the other step? Well, you represent the bonds using a line between 2 atoms. This line represents 2 electrons each. Here you have, for example, in the case of this compound, Br P, then you try, and you know that you have 3 Br, bromine, then you make single bonds between phosphorus, that is the central atom, and the 3 bromine. This line represents 2 electrons each. Then look at this. Sometimes we have what we call resonance structures. What does it mean? For example, in carbon dioxide, you have 16 electrons. You can represent, look, 1, 2, 3, 4, 5, 6, 7, 8. Well, you have the octet here. Then you have 2, 4, 6, and this 8. Then this carbon gets the octet rule 2. And in this case, oxygen, as you can see, has also the octet rule. But you can get this structure by resonance. What does it mean? That 2 of these electrons can be here. And then the structure that you have is 2 double bonds between carbon and oxygen. Look, 2 and 2 are 4, and 4 are 8. 8 electrons here and 8 electrons here. You have also the octet rule for every atom. Or you can have the other way. Look, octet rule, and octet rule. Then these 3 configurations are in resonance. What does it mean? That they are, the structure is going from one to another and returns, then they have the same possibility to be in the real life. They are in resonance. There are some exceptions. For example, boron does not get the octet rule. because it's not possible for boron since it is, as you can see, let's go back. As you can see here, boron is in the second period. Then it's only possible for boron to have 3 electrons, and it's okay for him. Sorry, not 4. This is incorrect. 3. It has 3 valence electrons, and it's okay this way for boron. Okay, let's go back. Boron is then one of the exceptions where boron does not get the octet rule. Look at this. This is the case of boron. And here we have the representation for every structure. Well, here you have the answer for every one. I'm going to develop, for example, this one. CCl4. Well, the central atom is carbon, of course, and carbon is in group 4, then it has 4 valence electrons, yeah? And fluorine is in group 7. Sorry, fluorine, no, chlorine is in group 7, then it has 7 valence electrons. As you have 4, what you do, you join this with 1 chlorine, here with 1 chlorine, here with 1 chlorine, and here with 1 chlorine. Carbon has 4 valence electrons and chlorine has 7. Since we have 4 fluorine atoms, then how many valence electrons we have at all? Well, we have 28 plus 4, 32. 32 valence electrons. Then what we do? We have here 2, 4, 6, 8. We already have 8 electrons. Then 32 valence electrons minus 8. We have still to represent 24 electrons. Then I begin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18, 20, 22, 24. And I represented the 24 valence electron. And look at this. This get the octet rule, same way with this chlorine, same way with this chlorine, and same way with this chlorine. But here you have 2, 2, 2, and 2, 8 electrons, then carbon also gets the octet rule. Then this structure is stable. Here you have that the only structure that have resonance is carbon dioxide. You have here another question. You can stop the video. You have the answer already. Now, let's see how can we represent the molecular structure in 3 dimensions. Look at this. Here we have this compound that is linear, while this one is trigonal planar because it's a triangle in a plane. And here we have the tetrahedral that has one atom in one direction, one in the other, one in the other, and one in the other, you have at least the 3 dimensions. So this is tetrahedral. These are 3 types of um, arrangement of the atoms in the space. Like see, for example, this is a linear structure. The angle of bond is, in this case, 180 degrees. This is carbon dioxide. So the molecule has this structure. This angle depends on in the in order to get the lowest repulsion between the electrons of this atom and this atom. Then the lowest repulsion between the electrons is getting the linear structure. Same way here. In order to get the least or the lowest repulsion between the electrons of the fluorine atoms is getting at 120 degrees. That's why this structure is trigonal, like a triangle, and they are in the same plane. All the atoms are in the same plane. And for the tetrahedral structure, well, the angle that makes possible the lowest repulsion is this one. The VSEPR, or in other words, valence shell electron pair repulsion, is a theory that is useful to predict the molecular structure that we can get. How? By minimizing the repulsion between the electron pairs, as we have seen before. For example, in ionic compounds, for example, for beryllium, the best structure in order to lower the repulsion from this electron and these electrons is getting the linear structure with an A180 angle of bond. In the case of boron, well, in order to lowest the repulsion between the electrons of these 3 fluorine is getting this structure in the space is like a triangle, and the angle of bond is 120 degrees. And as I showed you before, well, here in the case of methane, that is CH4, what the angle of bond is 109.5 degrees, and this structure is tetrahedral. Well, how can we predict the molecular structure using the VSEPR model? First, you draw the Lewis structure of the molecule. Then you count the electron pairs, arrange them in the way that minimizes the repulsion, and you put the pairs as far as possible. In order to later we determine the position of the atom from the way the electrons pairs are shared, and we determine the name of the molecular structure from the position of the atoms. For example, 2 pairs of electrons on a central atom in the molecules are always placed at 180 apart degrees. This is a linear arrangement. When we have one central atom and three atoms around, then the the atoms around the central atoms try to get a trigonal structure, and the angle is 120. If you have four atoms around the central atom, well, the best way is making the tetrahedral structure where the angle of bond is 109.5 degrees. When every pair of electrons on the central atom is shared with another atom, the molecular structure has the same name as the arrangement electrons pairs. But when one or more of the electron pairs around the central atom are unshared, what is the meaning? That they are lone pairs. The name of the molecule is different. Let's see what are these changes. For example, in the case of nitrogen and three pairs and three atoms of hydrogen, well, in this molecule, you have a lone pair of electrons. They are not shared with another atom. And then even though we have four groups of electrons around the central atom, it is not tetrahedral. The molecule is called trigonal pyramid because it's like a pyramid. And the angle of bond, well, is 109.5 if it were tetrahedral. In the case of water, for example, you have oxygen, but you have two lone pairs of electrons. Then you have one hydrogen here and one hydrogen here. Then, even though there are four groups of electrons around the central atom that is oxygen, this molecule, because of these two lone pair electrons, groups of electrons, this is V shape, is like a V, also known bent. The water molecule is bent. In the case of carbon dioxide, as we have seen, there are no lone pairs in the central atom, so it is linear. Well, here you have some examples of molecules, and you have the bonds, the angles of bonds, and the different structure for this molecule. You can stop the video and try to figure out this structure. Well, that's all in this class. There is a table that you can use. You can find this in the book where you can see according with the lone pair and the total of electron groups around the central atom, you can say if the molecule is linear or is trigonal, planar, or if it is tetrahedral. For example, just one example, look at this. In the case of CO2, we have two atoms, then we have two double bonds, and we have bonds, single lone pairs here, but we have to watch only the central atom. In this case, you have one group of electrons here, and here two groups of electrons. Then you have two groups of electrons, and you have zero lone pairs. You don't have lone pairs in the central atom. Then any molecule with two groups of electrons in the central atom and no lone pairs for sure will be linear. And the angle of bond will be 180. And so on. Then for molecules like this, phosphorus that has three groups of electrons around the central atoms, three groups, but there are no lone pair, these molecules will be trigonal pyramidal, and so on. Well, that's all. I hope that you understand. This is very, very, very important. See you soon.